Welcome everyone to the review session, the last lecture for the semester. I'm going to start in a minute or two. See, there's only 9 participants so far. I will not be teaching anything this summer because it's very time consuming. And I have to focus on my research a bit more. But I might be teaching something next year, like maybe not in the fall, but maybe next winter. Okay, so we wanted to go over this this discussion again. This was a discussion from the office hours. Let me just erase this. Yeah, and this is going to be part of the week 12 review session. Yeah, I guess it's better if I do this from scratch. Otherwise, I'll probably confuse myself, or it will be confusing to follow. So I'm just gonna erase everything. Okay. Any questions before we start? Any questions about the things we've learned up to this point this week? Okay, so this discussion is about finding the Jordan canonical form of a certain transformation, and all we know about the transformation is its characteristic polynomial. And before we find this, this is just to be 8. Well, this canonical form, just to remind you, is a form in which the matrix representing the transformation has a very simple form, and this is guaranteed to exist by this theorem. Now, the proof of this theorem, which we did yesterday, is very constructive. It basically says that we need to find invariant subspaces called the generalized eigenspaces. And the nice thing about these generalized eigenspaces, I mean, we've constructed them, we've just defined what they are, and then we've found that they have nice properties. But the book actually says that we need certain subspaces which are invariant and which only have one. When restricted to them, the transformation T has only one eigenvalue, and that's actually how they think about how they come up with this definition in the first place. But then when we have this, the key step in this proof, in this constructive proof, is to restrict the transformation, subtract the eigenvalues on the diagonal, and then you know that it has to be nilpotent. That's something that we've shown before. And then we can employ the nilpotent form for nilpotent matrices and the nilpotent transformations, which we covered in 6.2. And when we have this form, this canonical basis, we can build a basis for the whole vector space out of these bases of the generalized eigenspaces, because they are it is decomposed into a direct sum of these generalized eigenspaces. All right, so let me restart with this discussion. Right, so you need to find the Jordan blocks of T restricted to K lambda I for lambda I is equal to 2. The order should be 2. Oops. Lambda 1 is 2, lambda 2 is -1, and lambda 3 is equal to 5. We can also just notice right now the multiplicities of M1 is 3. So of lambda of the eigenvalue 2, the multiplicity is 3. The second multiplicity is 4, and the last one is 1. So let's just go in order, and let's start with the first generalized eigenspace. This is going to be okay. So we need the n of lambda 1 is T restricted to K lambda 1 minus lambda 1 times I, and we could really just restrict this whole transformation T minus lambda 1 I restricted to K lambda 1. But lambda 1 is just 2, so we really have T minus 2 I restricted to K lambda 2. Yeah, we keep calling this K lambda 1. Okay, and then this is a cycle tableau. That's the way that we get the canonical form. That's a question. So Joanna has a question, and I believe that this is taken care of in this proposition. So the dimension of the generalized eigenspace is exactly the multiplicity. So M is a multiplicity of lambda, and then the generalized eigenspace K lambda has dimension M. This is something that we proved yesterday. And this is exactly, I mean, if this wasn't true, then we know that so this statement here, that's a good question, because this is all interconnected. This idea here that we have dim v roots of the quadratic polynomial exactly says that so for eigenvalues lambda 1 to lambda k, this might be less than the dimension. But if we sum up the multiplicities of m lambda 1, m lambda 2, and so on, then this has to be the dimension of V. And then this is exactly, so we need this for V equals K lambda 1, this direct sum to be possible. Because if each K lambda 1 had a dimension of less than the multiplicity, then the dimension of the right-hand side here would be less than V, dimension of V. But the dimension of these has to be equal to the dimension of V. So you can go in and convince yourself that this is a crucial fact. Like this and this together is necessary for this to be possible. Okay, so right. So now we need to find the so now it's clear that the Jordan block of t restricted to k lambda 1 is given by the nilpotent form of n lambda 1. I never know how, like, if I should add more details. I could always add more details if it was up to me, but I need to eventually make move forward. So let me just say that the cycle tableau of the canonical basis, or sorry, there's not a unique one, of a canonical basis of n lambda 1 on k lambda 1. And this again, there's a statement, there's a reason why this exists. So we know that this exists. On k lambda 1 has dimension kernel n j minus dimension kernel n j plus 1 boxes in the jth column. So there's going to be something that looks like this. And this is the first column. This is the second column, and so on. And the number of boxes here has to be the difference between these kernels. That's a proposition that we had. We didn't prove it. The proof is in the book, but the result is very important. So now we need to compute. We need to compute what exactly is are the kernels of the powers of this nj. And so far, like probably the most confusing point of this discussion is that we don't even know what t is, and we don't know what this nilpotent transformation is, but we know we can compute the relevant kernels and the relevant numbers. So this means what we really want is these dimensions of the kernels, and the kernel of t minus, was it 2i of the first power is always just the eigenspace of 2. So the dimension of the first power of this is the n. It's just the eigenspace. And then when we go higher, this is really when we get interesting. Like, this is really when we have to do more work. So this is actually leave this open for now and continue writing the third kernel team. Oh, I forgot the power. 2i to the 3. Now, likewise, for the same reason that we know the first power of this kernel, because it's the eigenspace, we know that the highest power that we need to consider is the general's eigenspace itself. So this is k2. Yes. So yeah. Let me just write this as k2 because this is the first case lambda 1 equal to 2. Okay, so we know now we have to look in the exercise again and extract exactly these numbers. So this means we first use that it gives us the eigenspace E2 has dimension 1, and we know that the generalized eigenspace K2 has dimension M2, which is 3. This is how we extract the relevant dimensions of the kernels in the first for the first eigenvalue. So we know that this is 1 and this is 3. Now, yesterday I wasn't very I just said that we know now that this has to be 2, but there's a reason for this. And I've proven this, and I put this into as a discussion. Let me just find where Yeah, so discussion 9 for today's review session actually says that if n is nilpotent transformation V, then the kernel of the jth power has to be strictly less. Oh, I actually meant the dimension. The dimension of the kernel of the jth power has to be strictly less than the kernel of the n plus the jth plus first power for all j less than the index. If we have an index n, of course, n to the n plus 2 has the same kernel as n to the n plus 3, because once we reach n, the nth power, then it's 0 completely. So everything's in the kernel and we're done. But the interesting case is for the powers less than the index, where it's not exactly 0, but it has a kernel. And you can actually show that the kernel has to be strictly increasing in dimension. It can never be the same. Otherwise, we get a contradiction. And I hope we'll get to this discussion. I should probably hurry. No, honestly, I think there's too many discussions, but I'll just leave them as an exercise with you for preparation. Right. So here, for that reason, this discussion will actually tell us then that this has to be 2. And so we see now that the tableau will have to have the shape of just one box. There's from 0 to 1, the difference is 1. From 1 to 2, the difference is 1. And the difference from 2 to 3 is also 1. So this means we get a tableau that looks like this. So this is a tableau of just one cycle. And this means that the that in a canonical basis, the n2 looks like 0, 0, 0, 1. It doesn't matter what the basis is, and there are many bases. There's not like a unique one. And so now remember that n2 was just here exactly where we subtracted lambda times I, but now we just have to recover t. And this was actually, there was a discussion we had last week. So now in the same basis, t, and I should technically put these around here. We have that this is the same matrix plus lambda, the eigenvalue plus the identity matrix in this basis. So this would be just 2, 2, 2, 1, and 1. Are there now any questions about this procedure of finding the first Jordan block? Because this is going to just repeat itself 2 more times to find the other Jordan blocks. And if you have questions, we might as well talk about them right now. We can talk about the discussion 9 later. I just want to talk about this Jordan block for now. Okay, if there's no question, then I'm just going to repeat this whole thing for the next Jordan block. So we're going to have now the second case where lambda 2 is equal to, what was it, 5? Minus 1. Okay, so now we need to of t restricted to k minus 1. by computing the cycle tableau. Of a canonical basis of n-1, which is t minus -1, so it's t plus 1 I restricted to k minus 1. So again, what we need to do is we need to find the dimension of the kernel of t plus 1I. We need to find the dimension of the kernel of t plus 1I squared, and so on. Again, same as before, the dimension of the kernel of the first power of this operator is going to be the dimension of the eigenspace. And this is given in the question statement. So now this is here. So this is going to be 2. And this is given to be here we know that this is all of k minus 1 by question statement number 3. So here on the bottom it says that the restriction of this transformation to k minus 1 is 0 when we square it. So this means everything is going to tend to 0, and this means the kernel is all of the subspace. And if the kernel is all of this, then it means that the kernel is just a dimension of the dimension of k minus 1, even though two is less and not equal to the multiplicity of -1, which was 4. So usually we know that the highest, the multiplicity, if the power of this is the multiplicity of the eigenvalue, then we know that it's the whole Jonas eigenspace. But it can happen that this is already the whole eigenspace for a lower multiplicity, a lower power. So we know that this is equal to 4. And so the difference, the cycle tableau, is now from 0 to 2, it's 2 boxes for the first column. And then from 2 to 4, that's again 2 boxes for the second column. And so we have 2 cycles of length 2. And this means that the nilpotent transformation in some basis will have the form 0, 0, 0, and then just 2 cycles. So we have just these 2 nilpotent blocks of length 2. This was any questions about that, because we covered that last, I think, 2 weeks ago. Okay, I think the question was resolved. Okay, perfect. Right, and now, again, as before, we're not satisfied with just having the nilpotent transformation, because what we're actually looking for is the transformation itself. So the difference between the transformation and the nilpotent transformation that we computed from that in the same basis is just the eigenvalue multiplied with the identity matrix. But that just means that we will just exchange the zeros on the diagonal for the eigenvalue. And the eigenvalue here, remember, is -1. So that's why the Jordan block that we get for T is the same matrix, just with the diagonal now being the eigenvalues. Okay, so we almost done. The last case is very straightforward, because now we just do the eigenvalue lambda equals 5, but lambda equals 5 has multiplicity 1. So this means that T minus 5i, the restricted to the dimension of the kernel of this is the dimension of, let me start by saying, well, the multiplicity M5 is equal to 1. And this makes it very easy, because then the eigenspace E5 is equal to the generalized eigenspace K5. And this Jordan block, whenever this happens, the Jordan block is actually just a diagonal. And it's just a block of size 1 by 1. So I don't really have to do much computation anyways. I can already see, I could just jump the gun and say that, well, T in some canonical basis is going to be just 5. But the way that you would actually compute this is, well, the dimension of E5 has to be now 1, because we had this theorem that it's bounded above by the multiplicity, and this is 1, and it's bound below by by 1 as well. So this means we get just 1. This is the cycle tableau. And so in total, remember that the whole idea of this solve procedure is to decompose K into the generalized eigenspaces. This is a decomposition into invariant subspaces for T. And this means that T is equal to the direct sum of matrices. So in this, when we build now a basis for V out of the bases for the subspaces, and I've actually included a discussion later that answers a question that came up yesterday, why they will still be independent if they were independent in the direct summands. So if we now take a union of alpha, beta, and gamma, then there's a discussion to be made about why is this a basis of V if alpha, beta, gamma are bases of K2, K-1, and K5. But I'm not going to focus on this right now, because I think I've mentioned this before, and it's worth another discussion. Anyways, in this basis, we know that the matrix of T is just the direct sum of matrices. So we just have these different blocks together in a bigger matrix of the matrix from K restricted to the first generalized eigenspace, the alpha basis, second generalized eigenspace, and the last one. So this means now we can just put these building blocks together. And remember that these were, oh, I forgot. The first one was just one giant cycle. So this was 2, 2, 2. Okay. So this was 2, 2, and 2 with just one giant 3 cycle. The second one was 2, 2 cycles. So this means here's a 0. And the last one was just 5. And just putting them together means that we put them in a matrix as blocks. And it's going to look like this. We have 2, 2, and 2. We have -1, -1, and -1. Another -1. And then 5. There are ones, this is a 1, this is a 1, and that's it. I think someone also asked 2 weeks ago why I was considering this to be a one block, even though it's made up out of two subblocks. And this is, I guess, the answer, that even though it's the same eigenvalue, it might have different cycles within the same generalized eigenspace. Okay, that's finally the end of the discussion. Are there any questions? Oh, I noticed I set up my other camera and I didn't even use it. Oh, what is that? This looks funny. No. Let's go back to the FaceTime camera. Turn this off. No questions. Okay. Doesn't look like any questions. That was the end of week 11. And I have this discussion actually like repeated in the other discussion in week 12. Maybe one remark: if you have two matrices, then they are similar if and only if they have the same Jordan canonical form. That follows from the fact that the Jordan canonical form is unique, and the fact that it's unique is just because you have a recipe to compute it, and it depends only. It only depends on the characteristic polynomial. So on CT, I mean, with matrix CA of lambda, and the kernels of A minus lambda I to the J, which gives you the cycle tableau. And these two things, they're the same for B if B is similar to A. So changing to a similar matrix, you've seen before that the determinant and some such things are the same for two matrices which are similar. And we've also discussed that similar matrices have the same eigenvalues and things. So that's the reason why if the canonical form, the Jordan canonical form, only depends on these things, and they're the same for similar matrices, then similar matrices have the same canonical form. And at the reordering, well, I think there was a question, right? So if you have like a basis with the Jordan blocks maybe 1, 1, and 2, then if you reorder the basis, you could have the Jordan block up there. And of course, then they are different, and they're not. Then they are. Then they would have, even though these matrices are similar, they have a different canonical Jordan form. Canonical bases don't have to be, they can be vastly different. So if you look at the extras in the book, this is actually something that I would recommend you to look at. There's one at the end of 6 point of chapter 6, there's somewhere an exercise to find actually the basis. So far, we've always been concerned about finding the canonical form, but you could actually find the canonical basis as well, or a canonical basis. Remember, also compare this to diagonalization. If you have an eigenvalue with multiplicity 2, say, and you want to diagonalize the matrix, then you only have to find an eigenbasis of this matrix, but within an eigenspace, you can change the basis. So yeah, maybe let me find this first, and then I'll comment on this. Yeah, this is I would recommend to look at these two if you have questions about how to find the eigenbasis. So this clarifies it a little bit. So this is a good read. It's not necessary to read, but it helps you understand how you would find the actual basis of a certain tableau. Okay, so now the question that if you have no, maybe let me just this is a very detailed thing. I would rather get to discussions. Let me just say that if you have an eigenspace of dimension 2, then all you need, so say V is the eigenspace of lambda 1 plus E lambda 2, and this has dimension 2. So this is just a plane, it's just R2. Then you could find a basis of this and combine it with the basis of this. So this means that the basis of the whole space might be any basis of the first eigenspace and the second eigenspace. But you could easily just rotate these, and you get a completely different basis in the first eigenspace, and then combine it with the second. And so the eigenbasis or the canonical basis doesn't have to be a multiple of every other eigenbasis or so. Okay, so let's get to the week 12 material, which is just a giant review session with, I think, 14 or 12 discussions. This will cover anything that we've talked about in the textbook, all the sections that are included in the syllabus. And we'll not get to everything today, but we can just do a subset of these discussions, and the rest I'll just leave for you to work on as a preparation, as study material. Before we start, do you have any particular topics of this course that you would like to review? Like, say, any requests for a review? Okay, we can talk about fields. That's the one thing I didn't prepare anything for. But we could go back to, where was it? Was it I think it was, oh, am I still sharing? Oh, I think my window has changed. I think there was this. Yeah, we can. Was the discussion right? This discussion. We didn't do this discussion. Okay, that's actually in week 12. So let's start with that one. Discussion 14. So now we consider V, the real numbers, as a vector space over the field Q. And the question is the family of vectors 1 and square root of 2 linearly independent or dependent? What would you say? Yes, it's independent. And the reason is, if you try to find a combination that is zero, we need to verify whether there's some non-trivial such combination. So we try to find zero, but the zero vector is actually just the zero real number. So we want to have some alpha times 1 plus beta times square root 2, such that alpha, beta, non-zero. In what are alpha and beta elements of? Yes, that's very important, because if there were elements in R, of course we could just set alpha to be -1 and beta to be 1 over square root 2, and then we will be done. But that's exactly the point, that the scalars, this is the field of a vector space is always the place where the scalars live. So this is the set of allowed scalars in your computations. And now you can verify that this is equivalent to saying that minus alpha is equal to beta times square root 2, and this would mean that minus alpha over beta is equal to square root 2, but this is not in Q, and this would be in Q if alpha and beta are in Q. So this no such alpha beta can exist. And here I did a step that I have to justify actually. Why can I divide by beta? So I have to assume that so if beta is 0, the only solution is alpha equals 0. So assume beta is non-zero. And then I am allowed to do this step dividing by beta. But then I find that this leads to contradiction. And then this leads me to the conclusion only alpha equals 0, beta equals 0 solves this. And this means that this is linearly independent. Okay, what about number 2? What is the dimension of the subspace span of 1, square root 2, square root 3, square root 4? Yeah, so the question by Yuan, why Q not R? Well, I specified Q to be the field and R to be the vector space. Usually it's not such a confusing thing, because usually say R2, which is the tuples XY, is a vector space over R, and there's just numbers in there. And you would never confuse R and R2 because the one is tuples and the other one is just scalars, just single numbers. But if you have R and Q, the same distinction has to be made that the one are vectors, the other one are scalars. And all that you really need to do is you need to have some way that a scalar can multiply with a vector. That's true for this case. So you can multiply any real number with a tuple just by component multiplication. But it's also true here. You can multiply any real number with a rational number. It's just a coincidence that the rationals actually live inside R. So that's just a coincidence that we want to ignore. And it's usually very helpful if you are like if you don't be confused by coincidences in math. It's okay. So the dimension of this is 3. Why exactly would this be 3? Because this would mean that there are 3 independent vectors in there. Exactly. So the square root of 4 is actually 2. So this means well, remember that we had a theorem, a proposition that says we can let me make a new page. So the family 1, square root 2, square root 3, square root 4, which is just 2, is a family of vectors in the span of 1, square root 2, square root 3, square root 4, that spans the space. Let me maybe just give this a name, U. And then we had this reduced theorem by theorem. We can reduce, what should I call this? Maybe S. We can reduce S to a linearly independent family that still spans V. And the obvious candidate here is to kick out the 2. So we can check that 1, square root 2, and square root 3 is independent, and it still spans the whole space because square root 2 is a linear combination of these 3 vectors. And this means the dimension of V is the number of elements in the basis, which is 3. And the important thing here is, Jens, it was Zach wrote in the chat that what I just said, the 4 can be written as a linear combination of these elements. And the important thing is as a combination where the coefficients are rational numbers, because the coefficients always have to be in the field of the vector space. Okay, now the last question. Any ideas what, okay, this is unfortunate. Let me call this W instead. Oh, I called this U. I did call this U. Okay, that's good. So what about the dimension of V, which is just the whole space R? What's the dimension of this, of the real numbers as a vector space over Q? Yes, exactly. Because you can always find some other non-rational number such that it's not in the linear, not in the span of other, but in a family of vectors. So you would just do something like this, and then you just like take higher square roots of yeah, I'm not gonna want to make this precise. Any questions about this discussion? Any other requests of what we do next? Oh, there's the same slide again. So we could, did I prepare anything about Jordan forms? No, I mean, we just had that discussion about the Jordan form. So I didn't include anything else. I put this discussion in that the nilpotent transformation of V, then the kernel of what I would explained earlier. I think that's the only thing. Oh, I have this. This is, yeah, maybe this is good. So all matrices of size 2 by 2 in with complex entries are similar to either lambda 1, lambda 2, or to this other form. Any ideas about this discussion? Actually, let's take a break, and I'll let you think about this over the break, and then we'll answer this afterwards. Yes, Gen C's answer is good, and I'm going to elaborate on this after the break. So let's meet back here at 2:10, and then we'll resume with the review session. Please remind me to resume the recording. I'm going to pause this now. So the recording is rolling again, and I'll continue with the review session. So as Gen C just answered, all we really need is that C is closed, is algebraically closed. That's the important ingredient. So because C is algebraically closed, the characteristic polynomial CA of lambda will have two eigenvalues, lambda 1 and lambda 2. Now there's two options, two cases what could happen. So if lambda 1 is not equal to lambda 2, i.e. the multiplicity of m1 and of lambda 2 are both 1, then we know that A is diagonalizable. Just remember, because 1 is less or equal than the dimension of E lambda is less or equal than the multiplicity. So if both multiplicities are 1, then the dimension of the eigenspace is equal to the multiplicity necessarily, and it's diagonalizable. So this means that in some basis, or after some change of basis. Of basis, which is given by multiplying A with some change of basis matrix. This will be equal to lambda1, lambda2. Any questions about this first case? What happens if the multiplicity is, if they're not the same? So if they are the same, if lambda1 is equal to lambda2, then the multiplicity of m lambda, let's just call this lambda for simplicity. M lambda is equal to 2. So now we have to do even further division into cases. Then either the dimension of the is 2, or the dimension of E lambda is equal to 1. This can still both happen. So C guarantees us to have 2 eigenvalues, counting multiplicities, but it doesn't mean that it's diagonalizable. So if it's 2, then in this case we still have it's still diagonalizable. So this means in some basis QA, Q inverse is equal to lambda 0. If it's if the dimension of E lambda is equal to 1, then this means that the kernel of A minus lambda I has dimension equal to 1, and the dimension of the kernel of A minus lambda I squared, remember that this is the generalized eigenspace. This will have dimension 2 because the multiplicity is 2. So we so then we know that there is a then we know that A has canonical form lambda 1, because we have 1. So from this information we can get that the cycle of the tableau of A minus lambda I, which is nilpotent. Maybe I should write this first. So this is 2 cases. I should also maybe put a line between these. So here we can see that A minus lambda I is nilpotent with only eigenvalue lambda on C squared. There's a canonical nilpotent form of A minus lambda I is 0, 0, 1, because there's just one one two cycle in the cycle tableau. We just did exactly that computation. And this means that in some basis, in exactly that canonical basis for A minus lambda I, A is equal to lambda 1. But notice that the left case here, this is still captured in this is the same. So like this case 1 and case 2a, if you want to call this case 2a and this case 2b, this is still the same case. We never said here that lambda 1, lambda 2 have to be distinct. And actually, we can see from this that the these two matrices can't be similar. That could also be like a discussion. Show that that these two matrices are not similar. Well, they are already in canonical Jordan form, so we had the corollary that if they are similar, then they have to have the same form. Any questions? By the way, this file is already on my GitHub. So if you want to look through the discussions and pick one out that you like or that you want to see, then you can go to the GitHub that I linked on Quarkus. What other things do we have here? So let's just see. Just say stop when you see a discussion that you like. Here we just have something about subspaces. We have something about spans and linear combinations. The direct sum of symmetric and antisymmetric matrices, and we've talked about this before, but I thought this was a very neat discussion that involves a lot of things that are helpful. Yeah, we could. I think there was one about complex numbers. I remember I typed this up this morning, just everything that came to my head, everything that came to my mind, and there was one about complex numbers. Which one was it? This one. What are the real and imaginary parts of 1 over a plus ib? There's a long and a short solution, and you can either brute force this, or you can have one key idea that makes this a lot simpler. Any ideas how you would attack this question? Yes. Okay, Adrian knows the trick. Jagat, do you have an idea?
Actually, I had the same thing. So.
Oh, okay, the same idea. Yeah. So the nice thing is we can make this as a remark. Notice if you multiply, if z is equal to a plus ib in a complex plane, then we denote by z bar a minus b is the complex conjugate of z, and you could view this intuitively as just mirrored along the imaginary, no, sorry, the real axis. So if this is where the coordinate a is tracked, and this is b, then this is a plus ib. You can just think of the a, the x value, and b, the y value of this vector in R2. So this is, I mean, we introduced the complex numbers as being isomorphic to R2. And the nice thing is that in so there's a norm, or there's a length. The length of a vector in Euclidean geometry is just the square root of the entry squared. So xy in R2 has length x squared plus y squared. And this is just really due to if this is a vector, if this is xy, and this is the x-axis and this is the y-axis, then it is clear that this length L squared, this is supposed to be L, then L squared is equal to x squared plus y squared, but L is exactly the length. So it's just clear from Euclidean geometry, from the theorem of Pythagoras, that this is the length of a vector. But now notice that if you multiply a plus ib with its complex conjugate, which is a minus ib, so this is z times z bar, then the way that we multiplied them was we just multiply them as if they were all real numbers, that if this was a sum, a multiplication of a sum of real numbers with the I just having a special meaning. So we would have a times a, we would have a times minus ib, we would have plus ib times a, and we would have minus and we also have minus ib. You can see the aib cancels with the iba, and so we get a squared plus b squared, because we can also cancel the I times I for a -1, and then the minus is a plus. So you can see that the length of a complex number, the distance from the complex number to the origin here, is really just z times z bar square root. And the nice thing is this is a real number for all z complex numbers. My pencil's kind of giving up on me sometimes. Oh, did I resume? Yeah, I did resume the recording. It's just forgot that. Okay, so now why does it help to multiply with a complex conjugate? So notice that if you have 1 over z, then this is the same as z bar times z bar. But this is now z bar over the length of z squared. So yeah, I've kind of avoided the actual problem for so long now, and just made this more abstract than it has to be. So now let us use this all to observe what happens. Actually, the question is abstract too. Okay, so how do we get the real and imaginary part of 1 over a plus ib? Well, notice that 1 over a plus ib is equal to a minus ib multiplied in the denominator and numerator. This on the bottom in the denominator is now a squared plus b squared, a minus ab. And then we can just divide this fraction into a over a squared plus b squared minus I b a squared plus b squared. So all of this work, that all of the things I explained up here are basically just to say that there's a trick. Whenever you have a complex number and you want to multiply it with something to make it real, you just use the complex conjugate. That's the reason why we're able to get a real number in the denominator. And then, of course, we see that this is the real part and this is the imaginary part. Okay, any questions? Okay, other requests. Which one should we do next? There's seems like we're going backwards from the end. We could talk about this one. Two eigenvectors with different eigenvalues are linearly independent. Any idea how this will work? So we know that V and W can't be 0, otherwise they might they may not be eigenvectors. Yes. So a mix of both of the two answers are good. Jagat, do you want to say something?
Like we can just subtract the two equations and the result, like P of V bar minus P of W bar is equal to lambda I. Oh no. Sorry.
Okay, so the way that I mean, both answers in the chat are good. The way that you get a contradiction to this, I mean, you have to, of course, somehow show that this can't be true, that they can't be dependent. So the way that I would show this is you try to find a combination. And indeed, because we have just two eigenvectors, we can make this simpler. So we can suppose that V and W, the family of V and W, is dependent. This would mean that they have to be multiples. So in the case of a family of two vectors, they have to be multiples of each other for them to be dependent, because we already know that none of them is 0. So we can say that V is a multiple of W. And now what we can do is we can exactly do what Zach said. Well, if we apply T to V, we know that we get lambda times V. But if V is a multiple of W, we could just replace V with T of alpha times W. This is a linear transformation, so we can get the alpha out, and then we have T of W, which is alpha times sigma of W. But now, well, alpha times W is still V, so this is equal to sigma times V. So this means that lambda V minus sigma V is equal to lambda minus sigma V is equal to 0. So indeed, this is non-zero. So this means lambda would have to be equal to sigma. But we said that they have to be different. So they can only be dependent if the eigenvalues are the same. So this means that alpha, that V and W not multiples of each other. And this is exactly the same as saying that they are independent. And this is technically what Adrian wrote in the chat, that if they're dependent, they have to have the same eigenvalue. That's exactly this line here. It's just a matter of how do you start the proof so that you have like a consistent argument. And we could have worded the whole question differently. We could have said that V and W can only be dependent if they have the same eigenvalue. That would be the same idea. Jency requested to do discussion number 6 next. Any questions before we move to discussion number 6? Okay, let's see what discussion 6 is. Oh, yes. This is actually something that we haven't covered in the lecture, but it follows immediately from everything that we have done. So it's not that we skipped anything important, but this is a nice exercise that sums up a few properties that are worth reviewing. Okay, so the preimage of an element, is that a subspace or not? Any suggestions or guesses, or maybe y is non-zero, maybe it's 0. Does that change your answer? T minus 1 is the preimage. The preimage was defined. It's not the inverse of T. This is defined to be all the x in V. So first of all, T is a transformation from V to W. And then T inverse of Y for some Y and W is defined to be X and V, such that T of X is equals to Y. So it's all the vectors that are sent to exactly Y. Yes, so if Y is 0, the pre-image of 0 is nothing else but the kernel. Because I mean it's all the vectors X in V such that T of X is 0. This is the kernel of T, and this is definitely a subspace. We've shown this before. Now, in the other case, if Y is non-zero, this is not a subspace. Yeah, and that's actually a good proof by Matthew in the chat. So if Y is non-zero, then T inverse of Y does not contain 0, because T of 0 is 0 for all linear transformations, and not, I mean, yeah, it's clear then. If it's 0 and Y is not 0, then T of 0 can't be equal to Y. Okay, that's the answer of the first question. So it's a subspace if and only if the Y is 0. The second one, what does it say? So now we want to fix one vector x0 in the pre-image, and then we want to show that any other vector differs from x0 by something in the kernel. What exactly do we have to do to show this? Well, maybe another question of how to start is how many such Ks can there exist? So if we fix x0 and we pick another x, then then we can see that this K has to be unique. So we fix x0 once and for all in the pre-image of Y. Then for any other x in the pre-image, well, the K is just given by the difference. There is no other K. So K has to be just set to be x minus x0. And if we apply T to K, this is T applied to x minus x0. This is linear, so we can separate this to T of x minus T of x0. This is y minus y because they're both in the pre-image. So this is 0. And this implies that k is in the kernel of T. So this means, yeah, it was just a computation to show that that x is equal to x0 plus k for k in the kernel of T. Now, why exactly is this? Why exactly did I phrase it? Or why does the book phrase it like this? I forgot. 1 second. So the book actually talks about this somewhere. I believe it's just after like they talk about the kernel, so it should be easy to find. No, never mind. I can't find it immediately. But the idea is, let me just write something about the idea. So T inverse of y is isomorphic to kernel of T for all y in W. Remember still that T is a transformation from V to W. And this isomorphism is not unique. There are many isomorphisms. We can one of them is the assignment of k to k in the kernel of T to x in the pre-image of y, such that x is equal to x0 plus k for fixed x0. And I mean, it would probably be much better to write this just as T inverse of y going to the I just realized that this is not really, there's a problem with this. Can someone, this is also another good test question. Can someone see the problem with this? Why is what I just said, and I'm not joking, like this is a good exercise. If you can spot mistakes in someone's in someone's statements, then you get better at spotting mistakes in the things you think about yourself. So what's the problem with this isomorphism? And how can I fix it? That's the more important question. How can I save myself in the situation? Come on, someone has to tell me what's wrong with this. No, the dimension is actually fine. They're both the same dimension. It's more it's hiding in plain sight, so to speak. How did we define isomorphism? It's a linear transformation between vector spaces, right? Are those two things vector spaces? We just said that it's not a vector space, not a subspace if it does if the y is not zero. So this definition, I've just claimed that something's isomorphism between something that isn't even a vector space and a vector space. So that's the problem. It's not a vector space because it doesn't contain zero. It's something else, but I don't want to, like, I shouldn't talk about this right now. So what I can do to fix this is really it's bijective. But this sounds kind of weird. So I could say that there's a bijection between the pre-image of y and the kernel of t for all y in W. And I just to replace all the words isomorphisms with bijections. And now it is just, this is just a function of sets. But the interesting idea is here, yeah, a bijection is basically the an invertible function between two sets. So you don't even know whether the sets have to have an addition. I mean, remember, linear means you need to be able to add two vectors in the domain, in the codomain, for even to check that something's a transformation, so that something's linear. And if you have just sets, if you don't have a vector space structure on the domain or the codomain, it doesn't even make sense to pose that question. But why is this still an important thing to notice? Well, the kernel is a subspace. That much we know. So if we think about what really happens here is that every element, every vector in this subset, which is in subspace, is just translated by a fixed vector x0. So you can think of this as a plane, but it doesn't go through the origin. It's just a plane that is shifted, that's moved. So you could maybe draw this. So this is the x0. And if you have any other x in here, this difference actually lies in. So the difference between any two vectors, x and x0, lies in the kernel, meaning that it's a plane parallel to the kernel, to the subspace, which is the kernel. And the real reason why this is interesting, you can compare this with the following. Well, a solution space of ax equals 0 is null A. And likewise, we could say that this is the kernel of a transformation given by A. But if, so this is the case of a homogeneous system of equations, but the solution space of AX is equal to B of an inhomogeneous system, meaning that B is not equal to 0, is given by S consists of Y in Rn such that Y is equal to x0 plus x. Now I'm counting on your memory of the things you learned in 223, because this was a particular solution of AX equals to B. So you need to find one particular solution of this. And X is in X is a solution. Let me just write this again in the same style. So I hope you remember. Do you all remember this fact that a solution to a inhomogeneous system of equations is given by a homogeneous solution and any particular inhomogeneous solution? Or you could also say that any two solutions of the inhomogeneous system differ by a solution of homogeneous of the homogeneous system. Well, that's the same thing as I said above, only that the solution space to the homogeneous system is now called the kernel, and this this is actually the pre-image. This is the same as the pre-image. Pre-image to TA inverse of B, because you want exactly all the solution to the system is just all the vectors that are sent to B by this matrix A, or the transformation made by A. So you can think of this as a set of solutions to this homogeneous system. That's kind of the idea. That's the linear algebra behind this. Yeah, where's discussion 9? Oh, right. This is a good one. What was the best way of solving this again? Right. This is a quick solution to this. So the dimension of the kernel. So the proof just basically is a contradiction. Suppose not. Then for some j less than the index of n, the dimension of the kernel of n to the j is equal to the dimension of the kernel of n to the j plus 1. Since the kernel of n to the j is a subspace in the kernel of n to the j plus 1, because if you apply n to something that's already in the kernel another time, then it's sent to 0 as well. and proposition from before. This means that the kernel of n to the j is actually the same subspace. They don't actually have the same dimension. But remember that if you have two subspaces, one in the other, and they have the same dimension, they have to be the same spaces. So now I claim, so there's a few things we need to check. So first, the image of n to the j inside V is invariant under n. This is nothing complicated. It just this just follows because suppose you have x, you have x in here, then this means that x is just n applied j times to some other element y. But then if you apply n to x, the question is this still in the image? Well, we just write this as n applied to n to the j applied to y. This is n to the j applied to n of y. So this is still in the image of n to the j. Does that make sense? I'm now kind of going quickly because I want everyone to see this before it ends. But if you have questions, please slow me down. Maybe just intuitively clear that if you have something that's in the image and you apply it again, it's going to be in the image again. Here I actually mean as subspaces. And this is as real as numbers. Okay, so we have an invariant subspace, and then check that. So now the next step in this contradiction is to show the next step is to show that the kernel, if the kernel of n to the j is the kernel of n to the j plus 1, this means n to the j plus 1 of some vector x equal to 0 if and only if n to the j of this vector x equal to 0. So now what I want to show is I want to compute the kernel of n restricted to the image of n to the j. So what is that? Well, it is all the vectors in the image that are sent to 0. So x is in here if x is equal to n to the j for some y, and n of x is 0. So if n to the j of okay, so now compute n of x, this is n of n to the j of y. This is equal to n to the j plus 1 of y. And this is 0. Right, so this is 0 if and only if n to the j of y is 0, but n to the j of y was just x. So what we've shown is that the kernel of n restricted to the image of n to the j is trivial. So this means that the kernel of n restricted to the image of n to the j is trivial. But this is a problem. So now we come to the third bullet point. This is a problem. Because nilpotent transformation n going from v to v cannot have any non-trivial invariant subspaces on which n restricts to an isomorphism. And you can verify. Here we are in the case that the image of n to the j is non-trivial, is has non-zero, or I could say contains non-zero vectors, and therefore it's not non-trivial subspace because j is strictly less than the index of n. If n to the j was the zero subspace, then this would mean that the index of n would have to be j or less than j. But here it's greater than j strictly. So this means n to the j. I can just go on explaining to make this maybe more clear. So there's some v. There's some v in the image of n to the j, v non-zero, and we know that n of v, which is again in the image of n to the j, and n of v is non-zero. So now if you do this again, then n of v is non-zero, and we can just go on. Then n to the n of v is non-zero for all n, for all natural numbers. But this is a problem because eventually n to the n has to be 0 for all the vectors. 1 second, I just need to close the blinds. Yeah, this is exactly, so like the yellow and green stuff is exactly that explanation. I can go over it again. So basically, if you have a subspace, in this case, this is the image of n to the j, and you know that n restricts to this to be an isomorphism, then because it is non-trivial, there's some non-zero vector in the subspace. And if you apply n to this, it can't be zero because the kernel is trivial. So this means that n of v is again in the subspace and it's again non-zero. So you'll always have something in subspace such that if you apply n to this, it's something non-zero, something non-zero, something non-zero, and you can keep going forever. But this is clearly a problem because if this operator is nilpotent, some power of this, so if we keep going like this here, then we're going to have any number of n's applied to v, and this is going to be non-zero because v is in the image in the subspace on which n is an isomorphism. And I could just have I didn't have to say isomorphism. I could have restricts which n is injective. Because if you have a subspace that is injective for a nilpotent map, that's just a big problem. You can apply something to it, you can apply the n. Because it's invariant, you know that you're going to land back in the same subspace, and because it's injective on the subspace, you know that n applied to this one vector over and over again is going to be non-zero for eternity. But that's a problem because that contradicts this thing to be nilpotent. So why is the second? Yeah, why is this non-zero? Well, we started with something non-zero in the subspace. We know that n is injective on the subspace, and so it sends not something non-zero to something non-zero. But then we have something non-zero, and we just repeat the game. We say, okay, we apply n to something non-zero. It's injective. It produces something non-zero, and so it goes on and on and on. To be fair, I don't know if this is the simplest proof of this fact. I think it's a nice way of proving this. I find this elegant. But if any of you have like a simpler idea of how to prove this, you could message me and I'll include this in the notes. You could also maybe just put this on Piazza if you've found a better solution. Any other questions? Okay, if there are no questions, then I'll just leave the remaining discussions for you to use as preparation material. This is the end of the lecture and the end of the entire semester. I'm not sure why it's not the question. So if you have a direct sum of two subspaces, then yes, it has to be intersecting non-trivially. Sorry, trivially, yes. That's the definition. So if someone states that U and W, say, or a direct sum together to give another space, then they have to check before they make this statement that the intersection is trivial. Okay, that was the last question. Yeah, all right. So thank you guys too for coming to the lectures. It was really nice to teach this course, and I've enjoyed the lectures, not so much the preparation, but the lectures themselves. And I'm looking forward to teaching again. I don't know if I'm going to see you in another course again, but I also very much hope that your next course that you have will be on campus and in person. I don't know if any of you have never had an on-campus course. It's really much better than on YouTube or like on like online. And I wish you all of success for the test, the semester, and for your further studies. I don't actually know what majors you're taking, but maybe some of you will continue in math. If I've inspired one person in this audience to study more math, then I think I've achieved my goal. So enjoy the summer and best of luck for your further studies.
Thanks so much. Have a great summer.
Thank you. You too.
Thank you.
Thank you.
Thank you.
Thank you.
Goodbye, everyone.
Professor,
Yes.
I have just a quick question about the final. Like, it will include the entire syllabus, right?
1 sec. Let me stop the recording.